Hello students. Today we'll be discussing function transformations. This video is a continuation of our previous video, which we talked about coordinate transformations. And this topic is meant for students who are currently taking or who will be taking AP Calculus BC. If you look at the polar grid here, where the circles represent lines of constant r and the rays represent lines of constant theta, we'll see that there's a lot of radial or circular symmetry involved. What this means is that we can express functions that have circular symmetry in a highly simplistic way if we convert them from Cartesian to polar coordinates. Let's do an example with a circle. So in Cartesian coordinates, the equation of a circle is x squared plus y squared equals 1. Now, if you look at our coordinate transformation equations from last video, we notice that this is equal to r squared. So if we plug this into here, we'll have r squared equals 1, or in other words, r equals 1. So in effect, we go from a complicated equation in Cartesian coordinates to a very simple equation in polar coordinates. However, we don't always want to do this for every single equation. Let's look at an equation without this sort of symmetry, say a linear equation, y equals x minus 1. Now let's transform this into polar coordinates. If we use these equations right here, we'll see that this becomes r sine theta equals r cos theta minus 1. And if we do some rearranging, we'll see that r is equal to 1 over cos theta minus sine theta. So now, when we're dealing with a function without radial symmetry, we go from a relatively simplistic equation to something that's quite a bit more complex in polar coordinates. So in general, you really only want to do this if there's some circular or radial symmetry involved. That's it for this video. Thank you very much for watching this video and for watching our series on polar coordinates.